Welcome to the final 9th lesson. This one is unique, both because I'm going to touch an unusual subject of free will. So I want to connect what we learn about the mechanistic aspect of the brain and what we all feel, that we have free will to take this course. I have free will to provide you with this course. So let's talk about this later on. And so my plan for today is as follows. Basically, I want to summarize very, very briefly about what we've learned through this lesson, through this interaction among us, through the interesting interaction among us, which I will try to summarize at the end, say a few personal words. I want to touch on the whole subject of neuroethics. And so what is the implication of what you've learned about our brain in terms of ethical aspects? What does it mean ethically to have such a brain? So we'll discuss that, and especially questions like, are we going to be able to read our brain, our thoughts? Can I look at your brain and read your thoughts? What are the limits for brain intervention? When can I or should we as a society decide that this is something that needs an intervention? And when do we not want to intervene with the brain, Can we augment cognition? Can we make us better, so to speak, by intervention with our brain via pharmaceutical or electrical or other means? And all this, of course, the issue of brain reading, brain polygraphs, interventions with the brain for diseases, but maybe not only. These are ethical issues that emerge from modern brain research, which certainly we should discuss. This is not appropriate place in a complete sense, but I will still highlight a few issues that bother me, should bother all of us, and we should all discuss it together as a society. And specifically, I want to deal with some recent understanding of the whole very complicated, very, very delicate issue of, do we have free will? Am I free to choose, as I said, to come and lecture to you, to move my hand now, and so on. So the issue of free will be discussed later. And finally, at the end of this part, at the end of this lesson, at the end of this course, I want to discuss the new phenomena which Coursera is part of, the MOOC phenomena, MOOC phenomena, or other several related phenomena like the frontiers idea, which I'm part of, and the general open access idea for disseminating knowledge, transferring knowledge in an astute way to everybody who wants to listen, anywhere in the world, including you sitting in Iran, in Pakistan, in Alaska, anywhere in the world, listening online in an interesting way, hopefully, to what's going on in terms of human knowledge. This is a new phenomenon I would like to discuss, and then end with a farewell with a few personal words. So this is the plan for today, and let me start by reminding you how I did start this course. I started the course by citations of two people, Francis Crick, Nobel laureate, the genome. He was saying here, as I read in the first lecture, that we are only, no more than, synapses, molecules, everything we do, our feelings, our creativity, our action, our perception, everything comes from interaction of vast interacting molecules, networks, synapses, neurons, something that you know now, much better than you knew before, I hope. So this is a saying that means in many ways that we are a mechanistic machine, a physical machine, nothing more than a physical machine, a beautiful physical machine that generates beautiful things, especially feelings, create new things, sometimes terrible things, but it's a machine, and we needed to understand the machine both in order to understand ourselves, but also to repair ourselves, our brain, whenever it gets sick. Similar in different ways, I mentioned the saying of Claude Shannon, the father of information theory, we are thinking, yes, we are machine. We are living proof that we are physical machines. So we started by saying that in a general sense, but I started hopefully to teach you that indeed, when you look at the brain inside, you don't find any kind of miracles, any kind of spirits, any kind of, I don't know, other non-physical things, but you find practically, you find very, very, very physical things like genes, ions, membrane, channels, neurons, axons, networks, and eventually something comes out of it. Beautiful thing like love, but also terrible things like Parkinson. So I raised in the original question I raised, can we understand it? Can our own brain, with its own tools, mathematics, invention of tools to see things, to probe things, and you heard along the course about some new developments, like the clarity method that was invented while we were talking during this course. So we invent things because our brain is so plastic, so dynamic, so interactive, and so eager to do new things. This is very special to human beings, this issue of creativity. And we never touched, and we don't really understand what makes us so unique that we are so creative. But this is maybe for another course. So, can we understand? The answer is, of course, yes. We understand a lot. Do we understand everything? The answer is no. There is a lot of things to understand, a lot of fundamental issues that we don't understand. I'll touch about this a bit later on. But what did we learn in this course? What did we learn? So let me summarize what we learned very briefly. So to give you how I see the essential things I would very much like you to remember while you will contemplate on the beach with friends about this course. What did we learn? The first thing, again, that we are in unique times for brain research. These are really, really, for me, being in the field for 35 years, these are unique times in many aspects. One of the aspects is this development, is these new technologies. We mentioned the brain bow. We mentioned the connectomics. We mentioned the Human Brain Project, the European €1 billion Human Brain Project. We mentioned the BAM project, the Obama project, which is now called the Brain Project, so a little switch in the name. We mentioned the clarity, and we also mentioned, and that's something very important for me to emphasize, that all these techniques, wonderful techniques really, enable us to probe the brain and get huge, fantastic amount of data, new data, anatomical, physiological, combined anatomy and physiology, manipulative data like optogenetics and so forth. All this data requires a theoretical framework. So I emphasized several times, and I re-emphasize now, that without a theoretical framework, in trying to put all this data in some conceptual framework, that we can understand all this data so that we can really take the data and link it to higher level phenomena like emotions, like computation, like perception, requires theoretical efforts, requires theoretical framework. And so neuroscience now heavily depends on the development of new theoretical, mathematical concepts, tools that we are now trying to develop worldwide. So that's one message. The other message is that the elementary signals in the brain, electrical signals in the brain, are the spike, the action potential, initiated mostly in the axons, sometimes also in dendrites. We did not discuss it, but you should think about this output element of the nerve cell, the axon, as carrying bits of information, the spike, either there or not, 0 or 1, all or none, the spikes. This is a universal trick for action for the nervous system. Every cell, or almost every nerve cell, have this capability to generate or not generate the spike. So it's a universal trick, so to speak, for all nervous systems, from the lowest animal to the most sophisticated animal like you and me. The spike carries information, represents information in the world. So when I see a face, when you hear my voice, when I move my hand, there are spikes in particular neural networks, and these spikes represent whatever is represented, but also you use them to process this information through neural networks and eventually comes to an action, to a decision, to a creative idea, and so on. These are the spikes, and the other electrical signals carried by the nervous system are the postsynaptic potentials through the connection between the cells, the synapses. So you have two major electrical signals in the brain, the spikes mostly in the axons, the postsynaptic potentials mostly in the dendrites, and they converge one to the other via PSPs, many of them converging on the dendritic tree, eventually giving rise, if enough of them depolarize the axon, giving rise to a spike. And the connection between cells are the synapses, which are fantastic, unique device, enabling one cell, so to speak, to talk to the other cell via a chemical transmission between the spike in one side and the EPSP or IPSP, inhibitory or excitatory, on the other side. I also told you that underlying all these two signals, the spikes, the EPSPs, underlying these electrical signals is current flow through the membrane of these neurons. So these two key electrical signals, the spike and the postsynaptic potentials, are carried via very specific ion going through the membrane, either from inside outside of the membrane of the neuron or from outside inside. So these ions, charged ions, it could be sodium, it could be potassium, it could be calcium, these charged ions carry these signals. So these are the underlying microscopic currents that eventually give rise to the macroscopic phenomena of spike and postsynaptic potentials. The fourth summary, so to speak, or point, is that the input to cells, the converging input to cells, as I mentioned before, are the synaptic inputs. So synapses are the input to a cell, many of them helping the network to converge into a cell, a given neuron. So many thousand, sometimes 10,000 of synapses converge into a single cell, and this single cell, as a microprocessor, should take all this information from many synapses and making sense of it, so to speak, by generating spike output that reflects something about the input. So the neuron is an input-output microprocessor taking many synaptic input, converging onto its dendritic tree. They all sum, integrate, and eventually get to the soma, near the axon soma region where the spike output is generated. So the cell is a very sophisticated microchip with two separate regions, the input regions, the output region. In the input regions, there are many synapses impinging, converging, decorating the dendrite, and in the axon, there are these spikes output. The fifth point I want you to remember is that eventually, beyond speaking about the neuron as an input-output device, the input also participates in some computation. So when I talk to you now, when I see a visual line in the world, when I see a face, when I generate a voice, somehow these microchips and the network they are part of compute some aspect of the world. They need to compute the velocity of the car, they need to compute the weight of the glass, they need to compute the taste of the coffee, and so on. These are computations performed by single neurons which perform elementary computation, but eventually the network as a whole generate a computation that is essential for the behavior of the animal, of myself, of you. Without such computations, online and successful computations, we would not be able to survive. We and every other animal. So neurons compute from the information they collect, so to speak, from the environment, plus memory processes that during learning tell them what to do with this information so that the computation will become more and more efficient, more and more relevant, more and more adaptive, so eventually I will cross the road correctly without the car bumping into me. So this computational aspect, and the term computation borrowed from computer science, is of course more complicated than we think about, because it's not multiplying numbers. That's what the computer knows to do. It's not that. It's taking information from the environment and making a very sophisticated use of this information in order to be able to behave in this environment and also change this environment. So when I'm talking now, I'm not only computing what word should I say now, but I'm also changing you. Then you change me back with your blogs and feedbacks. So this is the perception action loop. And that's something I wanted really, really to emphasize, because this is so optimistic aspect of the brain, is that it's plastic. So neurons, and especially synapses. So the synapse is probably the most amazing material in the world, the synapse. Very minute, very plastic, wants to change, physically wants to change. And you now better understand what do I mean by saying change. Some of it is structural, so there are new synapses. Some of it is functional, so same synapses may become more or less efficient. So this change, this plasticity, really underlies the uniqueness of the brain. The total uniqueness of the brain and its capability to interact, change, adapt to the ever-changing environment. Ever-changing environment. So the plasticity aspect due to these synapses is really something absolutely miraculous in a sense of material. What kind of material it is that changes all the time. The best we know. And so we can use synapses in order to generate machines that learn, or at least the principles we learn from synapses, how to change with interaction while interacting with the environment. So synapses are really the miraculous aspect of the brain, is this capability to connect and to change adaptively. And final, and point number 7, just before the end of these 8 points. Overall, when I speak about the brain, when I'm talking now, when we're listening to you or to a music, or you listen to me, there are groups, large groups of neural networks. I mean millions, sometimes billions, that are now active electrically and chemically via the synapses. So this million of neuron networks, composed of million or billion of neurons, when something about the dynamical aspect of it, the electrical activity of it as a whole, operates within a regime that we call normal, so to speak, then I behave normally. I'm not sick with Parkinson. I'm not sick with schizophrenia. I'm not autistic. I'm not depressed. So large neural networks with a particular range of activity will enable me to behave normal, so to speak. It's a matter of definition what is normal. But the point is, when then these large neural networks somehow go out of balance due to connectivity within the network, or due to excitability that goes wrong within the network, or combination of many parameters go wrong, suddenly the whole network starts to generate a new phenomena, a new electrical phenomena, a new electrical activity, like in Parkinson, which you saw. Then the brain becomes disease. There is a disease. And a particular disease involves a particular system and a particular mechanism. And this is something, this emergence of disease, like emergence of some normal behavior, the emergence of large interactive group that emerge a particular activity that is normal or unnormal, not normal. This we don't really completely understand. We don't know how these elementary units, elementary aspects, together as a whole, generate a phenomena that we will call normal or not normal. And that's one of the really major challenge of neuroscience today. to try to go beyond the single cell, the single synapse, the single gene, and understand how a connected network of elements interacting now in my brain generate a disease, generate a feeling. So it's beyond the unit, it's the network. And for this, we absolutely need a theory for large elements interacting and generating dynamically and adaptively a phenomena that enables me to behave, or sometimes not, like in Alzheimer's. What's going on with the network in Alzheimer's? Why suddenly the network generates phenomena and activity where you forget things? Why in Parkinson the network suddenly generates this oscillation where I start to tremor? What's going on there? As a whole, we don't understand this. We don't even have good theory for it. So it's a big challenge for the 21st century, the century of the brain. So theory, again theory. So I can tell you about synapses, and I can tell you about genes, and I can tell you about spikes and EPSPs and inhibition and excitation, but how all this mechanistic aspect becomes a phenomena in a global sense. We need a theory for neural networks, a theory that connects the mechanistic aspect to the phenomena. Could be conscious phenomena, unconscious phenomena, could be disease, could be vision, perception. We don't know how to link these levels, and as I said, this is the biggest challenge of the 21st century. From gene neurons to the network level and the behavioral, phenomenological level. This is the biggest. And so I think the course actually tried to give you the basics. There will be course in psychology, which is the phenomena. There are no good yet course on the connection between, we don't understand this connection as yet, but there are some beginnings of understanding, and I hope that in the near future, some of the Coursera courses will touch on this connection, the theoretical aspect, theoretical neuroscience.